This is a video on the notes for energy changes in a chemical or physical process. This is a Google slide, and there will be information to obtain this Google slide if you'd like. The law of conservation of energy, which is the first law of thermodynamics, must be maintained when you have any kind of a change, either chemical or physical. And the first law of thermodynamics, or the law of conservation of energy, basically says that energy is maintained. So all the energy that goes in must come out. The other thing about energy is there must be an energy change. You can't have a change unless energy is somehow moving. And as we said before, or you'll hear in the future, most of the times you cannot measure the energy of something unless it is moving. When we discuss energy or thermodynamics, there are basically three things. There's a system, the thing that is actually going through the change. Then there's something called the surrounding, which is everything else in the universe. And then the universe, which is made up of the system and the surroundings. So the system can either release energy to the surroundings. Some people call it that it's losing energy. But of course, the first law would say that's not possible. You don't lose the energy. And what they really mean is that the system is releasing the energy to the surrounding. That is called exothermic. Or the system needs to absorb energy from the surrounding, and that's called endothermic. And these words are used both if you have a chemical reaction, which is, as you know from the kinetic molecular theory, the particles are rearranging to create new group sets, or a physical process where the particles are not rearranging, they are simply staying in the same group set. So both chemical reactions and physical processes can either be exothermic or endothermic. There must be one or the other. They can't be neither, because that would indicate that energy is not changing and it must change. So looking specifically at a chemical reaction where there is rearrangement of the base inside the base unit, what happens is, as you know from kinetic molecular theory, is that the particles, the base units, collide. And if they collide, and this is the word that you're supposed to use, if they have an effective collision, they collide effectively, they will rearrange or reorganize into new group sets. And for this to happen, you must have what is called an effective collision. And that effective collision requires two conditions. First, besides the energy, the potential energy that comes with all the reactants and how they're put together, you need an additional minimal amount of energy for a set of reactants to rearrange or to form a set of new products. That's called the activation energy. And I abbreviate it with a big E and a subscript AC, which you'll see in a subsequent slide. That's only the first thing. The second thing is you need the correct spatial coordinates, of the reactants. And that takes kind of two forms. One, they have to be close enough together to actually collide. And second of all, if they're close enough together, they have to be in the right three-dimensional orientation to each other. So those are the two requirements. And if you don't have either one of them, what will happen is they will collide and they'll just simply stay the way they are and they fall apart, and you do not have a chemical reaction. So what happens after you effectively collide? What happens is they stick together for a very, very short period of time, let's say a billionth of a second or so, and they come together as one entity with all the atoms of all the reactants and all the energy of all the reactants, called the potential energy of the reactants, plus the energy of the activation energy. And they all are together, and we call that the activated complex. And if you have that, it will then fall in a billionth of a second or less. It will fall apart, and as it falls apart, the atoms rearrange themselves into new group settings, and those group settings need energy to stick together, and that's called the potential energy of the products. So there are two diagrams to explain these two conditions. They're both called the potential energy diagram. This is the potential energy diagram of an exothermic reaction or process. Potential energy is on the left-hand side, on the y-axis, which is also called enthalpy a lot of times. And then you have this weird x-coordinate they're called the reaction coordinate. And basically what the reaction coordinate is three locations. The farthest left is the reactants, the farthest right is the products, and then in between, in the middle, is the activated complex. And as you can see, for this particular exothermic reaction, which we'll talk about in the next slide, the potential energy of the reactants is greater than the potential energy of the products. Even though that's the case, we still need a minimum amount of energy to make an effective collision, and that's what the activation energy is. And right at the top of the hill, where you have the up arrow for to show the activation energy, that's the point of the activated complex. And the potential energy of the activated complex goes all the way down to the x-axis. That includes the activation energy plus the potential energy of the reactants. And when the effective collision happens and the particles reorganize themselves into the products, those products need to have energy in it called the potential energy of the products, and that's the right-hand side. As you can see, there's a difference between the potential energy reactants and products. That's called the heat of reaction, delta H. And for an exothermic reaction, that is a negative sign, because the negative sign indicates that that energy is going to be released from the system to the surrounding, because when the when the products were formed, they only used some of the energy that came from the potential energy of the reactants and the activation energy. So there's some left over, so they emit that energy. They release that energy. So the activated complex is on top of the hill. It includes all the atoms and all the energy. And the second part, the potential energy of the reactants is greater than the potential energy of products. This is the reason why the energy is being released from the surroundings. Delta H is a negative value. It's also the reason why the system only needs help from the outside with one activation energy, because for the second set of reactants we form products, it steals some of that extra energy that's being released for the activation energy of the second set, and so on and so on and so on. That's why an exothermic reaction like a match, you only strike the match once. The friction from the match going across that material is the activation energy the first time, and then the reaction keeps on going because it's stealing some of the energy that's being released as the activation energy for subsequent sets of reactants to form sets of products. That's not true of an endothermic reaction. The endothermic reaction is the opposite. Potential energy of reactants is actually less than the potential energy of the products. The activation energy still exists, and the heat of reaction still exists. This time it's positive. And what happens here is the system needs to add in energy to get up to the potential energy of the products. So when you have an effective collision and the reactants, the activated complex falls off.
If Hirsch Pandy is in the building, please come to the high school office. Hirsch Pandy to the high school office. Thank you.
So when the activated complex falls apart and the products we reorganize to make the products, they need energy. But what it is they need more energy than the reactants or the activated complex has. So it needs to put energy in. That's why in endothermic reaction, you need to put activation energy in, or energy in constantly for one set of reactants to form products. And for the next set, you have to put energy in. And if you don't put that energy in, i.e. the system absorbs the energy from the surroundings, the reaction stops. It has a delta H that is in the positive value. So if you look at the bottom, the potential energy of the reactant is less than the potential energy of the product for an endothermic reaction. So the system needs to absorb energy basically constantly to get the energy it needs at a minimum for the activation energy to form the products. And if they don't get it, the reaction stops, like boiling water. If you don't put energy in to boil the water, to make the water go from a liquid to a gas/vapor phase, it's not going to happen. So those are the two types of energy transfers or change in a chemical process or a chemical reaction. Thank you.